Before we get to multiplying and dividing square roots, there's one more thing we need to talk about with what happens when your radicand has variables. Well, if your radicand has variables, it's actually pretty easy to deal with, but there is some very important detail you have to take care of, right? Because when we talk about this symbol right here, that means the positive square root, right? So if I say, what's the square root of x squared, your first thought is, well, it's x. Well, that's a problem because we're saying this has to be the positive square root. Is x a positive value? Well, x can take on any value. You can't guarantee that x is positive just saying, well, trust me, it's x, it's positive. So what we have to do in a situation like this is we have to make sure that we have absolute value around that. Right? That absolute value makes sure that our answer is positive. And we only have to do this with variables. We don't worry about this with numbers because we know if numbers are positive or negative. If I write the number 6, that's a positive value. I don't have to write, oh, by the way, it's the absolute value of 6. Yeah, we get it. It was positive to begin with. You didn't have to do that. But a variable like x, well, that's a different story. You don't know if that's positive or negative. And we have to guarantee if it's a principal square root, it definitely has to be positive. Right? So something like the square root of x to the 6. Again, any even power is a perfect square. So 2 is a perfect square, 6 is a perfect square. So it should come out nice, and it does. This will be x to the third, right? Because x to the third times x to the third is x to the 6th. That's why x to the 6 is a perfect square. Now, can you guarantee x to the third is a positive value? The answer is no, you cannot. X to the third, you take a number to the third power, is it positive? Could be, but it doesn't have to be. So again, we need an absolute value. Now, before you start thinking everything that has a variable is absolute value, that is definitely not true. We'll hit that third example here in a minute. If I had the square root of x to the 4th, for example, well, this will be x squared. Now, the question is, can I guarantee that x squared is positive? The answer is yes, I can. Because when you square a number, it will always be positive. So putting absolute value around that is kind of like overkill. It's not necessary, and we don't write it if it's not needed. We need it basically when our exponents turn out to be odd. So if we have a perfect square where it starts off even, and that's what makes for a perfect square. And after we do the square root, we get x to an odd power. That's when we have to have the absolute value. So we had an even here for sure, but then we had an even again. And an even power will guarantee that it is positive. So putting absolute value, like I said, it's overkill. It's not necessary. It's like putting absolute value around 6. You don't need absolute value around 6. We already know it's positive. Right, so let's get a bigger number. Say we had the square root of x to the 24th. What's the square root of x to the 24th? Well, is x to the 24th a perfect square? It sure is. Is x squared times, or x to the 12th times x to the 12th? So we would say this is x to the 12th. Now my question is, can you guarantee x to the 12th is a positive value? The answer is, yeah, you can. Because it's to an even power, we do not need absolute value on this. Whereas if I did something a little bit off, like the square root of x to the 34th, well, that would be x to the 17th, but x to the 17th is not guaranteed to be positive. We have to guarantee it's positive by putting absolute value. So if your powers go even, then odd, for variables only, that's when you need the absolute value. So even, then odd is an absolute value. Even, don't need it. And if it starts off odd to begin with, it definitely does not need it. You don't put absolute value around anything that starts off with an odd power in your radicand. Because if they're putting an odd power in their radicand, they better make darn sure that x is not negative, because they're presenting the problem right here. If x is negative, you have issues with this one, because you can't take the square root of a negative value, which is what x to the 13th would be. Now the question is, how do you do this? Well, you do this simply like we did before. We say, okay, What is the largest perfect square that divides into x to the 13th? That's x to the 12th. It's x to the 12th times x to the first. The square root of x to the 12th times the square root of x. Well, square root of x to the 12th is x to the 6th. Square root x. You don't worry about absolute value if your radicand power starts off odd. The only time you have to worry is if your radicand power starts off even and the result is an odd power. That's the only time we ever use an absolute value. So you can make a general rule for these. If you take the square root of x, and I put in the word even, saying x to an even power, and the result comes out to be x to an odd power, whatever that might be, this is the one and only time you have to use absolute value. So the square root of x to an even equals the square root of x to the odd. If you have that scenario like we did here, 2 and 1, 6 and 3, we need absolute value. 34 and 17, same thing. But if it's even, no absolute value is necessary. In fact, it's overkill. And if it starts off odd, forget it. There's no absolute value even to consider, no matter what. Right? So that's how we simplify with the variables. Now, as far as the multiplication is concerned, the multiplication rule that we used before, we're going to use again. Basically in reverse. What we used before is we said if we have the square root of a product, well, we can split that up into 2 square roots. In fact, that's how we simplified our square roots. So we would divide this up into the largest perfect square times some other number. Right? Well, this works in reverse. If you have 2 square roots that are being multiplied together, we can join them together as one giant radicand. So the property is obviously reversible. So let me give an example of a situation. Let's see, I'll steal mine here. Say 3 square root of 5, 2 square root of 10. So 3 square root of 5 multiplied by 2 square root of 10. Okay, if we multiply these together, what we're going to do, since it's 3 and 2 on the outside, we're just going to multiply those together to get 6, and then square root of 5 times square root of 10, you have the square root of a times the square root of b, put it back together as the square root of 50. Now, of course, you got to look at your final answer and say, is that completely simplified? The answer is no, because what is the largest perfect square that divides into 50? That is 25. So 25 multiplied by 2, so we call this 6, square root 25, square root 2, or 6 times 5 times the square root of 2. So we get 30 square root of 2 for our final answer. So that's kind of how we would handle a problem like that. Let's see. Okay, why don't we take something like the second one here. Let's say we had the square root of 44. X to the 8th, y to the 3rd. And let's throw in z. Z to the 18th. Now, problems like this tend to intimidate students because, you know, this monomial 44x to the 8th, y to the 3rd, z to the 18th, that's bad enough. And then throwing a square root on top of that, making this the radicand, it just seems incomprehensible sometimes. But the idea is we're just using this simple rule. Now, in this case, we already have the product. We're splitting this back up into easier parts. So turn this into 4 simpler problems. That would be the square root of 44, the square root of x to the 8th, square root of y cubed, and the square root of z to the 18th. So 4 simpler problems that we're just going to multiply back together here. So what is the square root of 44? Well, what is the largest perfect square? I think it's just 4. So let me actually split that up into the 2 parts that it is. So I'm just going from here right to there, 4 and 11. Well, the square root of x to the 8th, that is a perfect square. That would be x to the 4th, even, no absolute value. Now this starts off odd, so I'm not worried about it. But if you think about y cubed, it's y squared times y to the first. So we have a y square root y. And again, no absolute value. Even though that's an odd power, it doesn't matter. It started off odd to begin with, so we forget it. Z to the 18th, that's a perfect square. That's z to the 9th. 9 is odd, so we do need absolute value. All right, so to clean up this final answer, let's just try to do this all in one move. That's 2. Square root of 4 is 2, so we're going to write 2, and then we'll go with all the variables on the outside. So we'll say an x to the 4th, y to the 1st, absolute value z to the 9th, and then just use this property where we have individual square roots. We're going back and putting them together. So we have an 11 times y, or our final radicand will just be 11y. So that's how we would simplify a mess like that using this rule, actually in both directions. Right? Anything else? We could try one more, just that seems to bother people. Say we had a 7 square root of 3 to the second power. Right? Now, understand how we do this. We just have to interpret what taking something to the second power is. It just means multiplying it by itself. So a 7 square root of 3 times another 7 square root of 3. And what you can see is it just goes back to something like this. We'll multiply the 7's together to get 49. And we have the square root of 3 times 3, which is 9. So you have 49 times 3, which I think is 147, if I do the math correctly. So handle the exponents just as you would, just interpret it as times itself.